IEEE 802.11 is a set of media access control and physical layer specifications for implementing wireless local area network computer communication in the 2.4, 3.6, 5 and 60 GHz frequency bands. They are created and maintained by the IEEE LAN Standards Committee. The base version of the standard was released in 1997 and has had subsequent amendments. The standard and amendments provide the basis for wireless network products using the Wi-Fi brand. While each amendment is officially revoked when it is incorporated in the latest version of the standard, the corporate world tends to market to the revisions because they concisely denote capabilities of their products. As a result, in the marketplace, each revision tends to become its own standard. General description: the 802.11 family consists of a series of half-duplex over-the-air modulation techniques that use the same basic protocol. 802.11-1997 was the first wireless networking standard in the family, but 802.11b was the first widely accepted one, followed by 802.11a, 802.11g, 802.11n and 802.11ac. Other standards in the family are service amendments and extensions or corrections to the previous specifications. 802.11b and 802.11g use the 2.4 GHz ISM band, operating in the United States under Part 15 of the U.S. Federal Communications Commission rules and regulations. Because of this choice of frequency band, 802.11b and g equipment may occasionally suffer interference from microwave ovens, cordless telephones and Bluetooth devices. 802.11b and 802.11g control their interference and susceptibility to interference by using direct sequence spread spectrum and orthogonal frequency division multiplexing signaling methods, respectively. 802.11a uses the 5 GHz UNII band, which, for much of the world, offers at least 23 non-overlapping channels rather than the 2.4 GHz ISM frequency band, where adjacent channels overlap. See list of WLAN channels. Better or worse performance with higher or lower frequencies may be realized, depending on the environment. The segment of the radio frequency spectrum used by 802.11 varies between countries. In the U.S., 802.11a and 802.11g devices may be operated without a license, as allowed in Part 15 of the FCC rules and regulations. Frequencies used by channels 1 through 6 of 802.11b and 802.11g fall within the 2.4 GHz amateur radio band. Licensed amateur radio operators may operate 802.11bg devices under Part 97 of the FCC rules and regulations, allowing increased power output but not commercial content or encryption. History: 802.11 technology has its origins in a 1985 ruling by the U.S. Federal Communications Commission that released the ISM band for unlicensed use. In 1991 NCR Corporation AT&T invented the precursor to 802.11 in Nijmegen, the Netherlands. The inventors initially intended to use the technology for cashier systems. The first wireless products were brought to the market under the name WLAN with raw data rates of 1 Mbps and 2 Mbps. Vic Hayes, who held the chair of IEEE 802.11 for 10 years and has been called the father of Wi-Fi, was involved in designing the initial 802.11b and 802.11a standards within the IEEE. In 1999, the Wi-Fi Alliance was formed as a trade association to hold the Wi-Fi trademark under which most products are sold. Protocol: A1A2 IEEE 802.11y 2008 extended operation of 802.11a to the licensed 3.7 GHz band. Increased power limits allow a range up to 5,000 am. As of 2009, it is only being licensed in the United States by the FCC. B1B2 assumes short guard interval enabled, otherwise reduce each data rate by 10%. 802.11-1997. The original version of the standard IEEE 802.11 was released in 1997 and clarified in 1999, but is today obsolete. It specified two net bit rates of 1 or 2 megabits per second, plus forward error correction code. It specified 3 alternative physical layer technologies: diffuse infrared operating at 1 bit s, frequency hopping spread spectrum operating at 1 bit s or 2 bit s, and direct sequence spread spectrum operating at 1 bit s or 2 bit s. The latter two radio technologies used microwave transmission over the industrial scientific medical frequency band at 2.4 GHz. Some earlier WLAN technologies used lower frequencies, such as the US 900 MHz ISM band. Legacy 802.11 with direct sequence spread spectrum was rapidly supplanted and popularized by 802.11b. 802.11a. Originally described as Clause 17 of the 1999 specification, the OFDM waveform at 5.8 GHz is now defined in Clause 18 of the 2012 specification and provides protocols that allow transmission and reception of data at rates of 1.5 to 54 bits. It has seen widespread worldwide implementation, particularly within the corporate workspace. While the original amendment is no longer valid, the term 802.11a is still used by wireless access point manufacturers to describe interoperability of their systems at 5.8 GHz, 54 bits. The 802.11a standard uses the same data link layer protocol and frame format as the original standard, but an OFDM-based air interface. It operates in the 5 GHz band with a maximum net data rate of 54 bits, plus error correction code, which yields realistic net achievable throughput in the mid-20 bits. Since the 2.4 GHz band is heavily used to the point of being crowded, using the relatively unused 5 GHz band gives 802.11a a significant advantage. However, this high carrier frequency also brings a disadvantage. The effective overall range of 802.11a is less than that of 802.11bg. In theory, 802.11a signals are absorbed more readily by walls and other solid objects in their path due to their smaller wavelength and, as a result, cannot penetrate as far as those of 802.11b. In practice, 802.11b typically has a higher range at low speeds. 802.11n also suffers from interference, but locally there may be fewer signals to interfere with, resulting in less interference and better throughput. 802.11b. The 802.11b standard has a maximum raw data rate of 11 bits and uses the same media access method defined in the original standard. 802.11b products appeared on the market in early 2000, since 802.11b is a direct extension of the modulation technique defined in the original standard. The dramatic increase in throughput of 802.11b along with simultaneous substantial price reductions led to the rapid acceptance of 802.11b as the definitive wireless LAN technology. Devices using 802.11b experience interference from other products operating in the 2.4 GHz band. Devices operating in the 2.4 GHz range include microwave ovens, Bluetooth devices, baby monitors, cordless telephones and some amateur radio equipment. 802.11g. In June 2003, a third modulation standard was ratified, 802.11g. This works in the 2.4 GHz band, but uses the same OFDM-based transmission scheme as 802.11a. It operates at a maximum physical layer bit rate of 54 bits exclusive of forward error correction codes, or about 22 bits average throughput. 802.11g hardware is fully backward compatible with 802.11b hardware and therefore is encumbered with legacy issues that reduce throughput when compared to 802.11a by 21%. The then proposed 802.11g standard was rapidly adopted by consumers starting in January 2003, well before ratification, due to the desire for higher data rates as well as to reductions in manufacturing costs. By summer 2003, most dual-band 802.11 AB products became dual-band tri-mode, supporting A and BG in a single mobile adapter card or access point. Details of making B and G work well together occupied much of the lingering technical process. In an 802.11G network, however, activity of an 802.11B participant will reduce the data rate of the overall 802.11G network. Like 802.11B, 802.11G devices suffer interference from other products operating in the 2.4 GHz band, for example wireless keyboards. 802.11-2007, in 2003, Task Group TGMA was authorized to roll up many of the amendments to the 1999 version of the 802.11 standard. RevMA or 802.11 MA, as it was called, created a single document that merged 8 amendments with the base standard. Upon approval on March 8, 2007, 802.11 RevMA was renamed to the then current base standard IEEE 802.11-2007. 802.11n. 802.11n is an amendment which improves upon the previous 802.11 standards by adding multiple input multiple output antennas. 802.11n operates on both the 2.4 GHz and the lesser used 5 GHz bands. Support for 5 GHz bands is optional. It operates at a maximum net data rate from 54 Mbps to 600 Mbps. The IEEE has approved the amendment and it was published in October 2009. Prior to the final ratification, enterprises were already migrating to 802.11n networks based on the Wi-Fi Alliance's certification of products conforming to a 2007 draft of the 802.11n proposal. 802.11-2012, in 2007, Task Group TGMB was authorized to roll up many of the amendments to the 2007 version of the 802.11 standard. REVMB or 802.11 megabytes, as it was called, created a single document that merged 10 amendments with the 2007 base standard. In addition, much cleanup was done, including a reordering of many of the clauses. Upon publication on March 29, 2012, the new standard was referred to as IEEE 802.11-2012. 802.11 AC. IEEE 802.11 Act 2013 is an amendment to IEEE 802.11, published in December 2013, that builds on 802.11n. Changes compared to 802.11n include wider channels in the 5 GHz band, more spatial streams, higher order modulation, and the addition of multi-user MIMO. As of October 2013, high-end implementations support 80 MHz channels, 3 spatial streams, and 256 QAM, yielding a data rate of up to 433.3 Mbps per spatial stream, 1300 Mbps total, in 80 MHz channels in the 5 GHz band. Vendors have announced plans to release so-called Wave 2 devices with support for 160 MHz channels, 4 spatial streams, and MIMO in 2014 and 2015. 802.11 AD. IEEE 802.11 AD is an amendment that defines a new physical layer for 802.11 networks to operate in the 60 GHz millimeter wave spectrum. This frequency band has significantly different propagation characteristics than the 2.4 GHz and 5 GHz bands where Wi-Fi networks operate. Products implementing the 802.11 AD standard are being brought to market under the WeGig brand name. The certification program is now being developed by the Wi-Fi Alliance instead of the now defunct WeGig Alliance. The peak transmission rate of 802.11 AD is 7 Gbps. 802.11 ARF. IEEE 802.11 ARF, also referred to as Wi-Fi, and Super Wi-Fi, is an amendment, approved in February 2014, that allows WLAN operation in TV white space spectrum in the VHF and UHF bands between 54 and 790 MHz. It uses cognitive radio technology to transmit on unused TV channels, with the standard taking measures to limit interference for primary users, such as analog TV, digital TV, and wireless microphones. Access points and stations determine their position using a satellite positioning system such as GPS and use the Internet to query a geolocation database provided by a regional regulatory agency to discover what frequency channels are available for use at a given time and position. The physical layer uses OFDM and is based on 802.11 AC. The propagation path loss as well as the attenuation by materials such as brick and concrete is lower in the UHF and VHF bands than in the 2.4 and 5 GHz bands, which increases the possible range. The frequency channels are 6 to 8 MHz wide, depending on the regulatory domain. Up to 4 channels may be bonded in either one or two contiguous blocks. MIMO operation is possible with up to 4 streams used for either spatial time block code or multi-user operation. The achievable data rate per spatial stream is 26.7 Mbps for 6 and 7 MHz channels and 35.6 Mbps for 8 MHz channels. With 4 spatial streams and 4 bonded channels, the maximum data rate is 426.7 Mbps for 6 and 7 MHz channels and 568.9 Mbps for 8 MHz channels. 802.11r. IEEE 802.11r defines a WLAN system operating at sub-1 GHz license-exempt bands, with final approval slated for March 2016. Due to the favorable propagation characteristics of the low-frequency spectra, 802.11r can provide improved transmission range compared with the conventional 802.11 WLANs operating in the 2.4 GHz and 5 GHz bands. 802.11r can be used for various purposes including large-scale sensor networks, extended-range hotspot, and outdoor Wi-Fi for cellular traffic offloading, whereas the available bandwidth is relatively narrow. 802.11i. IEEE 802.11i is an amendment to the 802.11 standard which will add new mechanisms for a faster initial link setup time. 802.11arg. IEEE 802.11arg is a rebanding of 802.11 AD for use in the 45 GHz unlicensed spectrum available in some regions of the world. 802.11 AC. IEEE 802.11 AC is an amendment to the 802.11 standard which will enable pre-association discovery of services. This extends some of the mechanisms in 802.11 new that enabled device discovery to further discover the services running on a device, or provided by a network. 802.11 AX. IEEE 802.11 AX is the successor to 802.11 AC and will increase the efficiency of WLAN networks. Currently at a very early stage of development, this project has the goal of providing 4x the throughput of 802.11 AC, channels and frequencies. 802.11b, 802.11g, and 802.11n 2.4 utilize the 2.400 or 2.500 GHz spectrum, one of the ISM bands. 802.11a and 802.11n use the more heavily regulated 4.915 or 5.825 GHz band. These are commonly referred to as the 2.4 GHz and 5 GHz bands in most sales literature. Each spectrum is subdivided into channels with a center frequency and bandwidth, analogous to the way radio and TV broadcast bands are subdivided. The 2.4 GHz band is divided into 14 channels spaced 5 MHz apart, beginning with channel 1 which is centered on 2.412 GHz. The latter channels have additional restrictions or are unavailable for use in some regulatory domains. The channel numbering of the 5.725 or 5.875 GHz spectrum is less intuitive due to the differences in regulations between countries. These are discussed in greater detail on the list of WLAN channels. Channel spacing within the 2.4 GHz band, in addition to specifying the channel center frequency, 802.11 also specifies a spectral mask defining the permitted power distribution across each channel. The mask requires the signal be attenuated a minimum of 20 decibels from its peak amplitude at a plus or minus 11 MHz from the center frequency, the point at which a channel is effectively 22 MHz wide. One consequence is that stations can only use every fourth or fifth channel without overlap. Availability of channels is regulated by country, constrained in part by how each country allocates radio spectrum to various services. At one extreme, Japan permits the use of all 14 channels for 802.11b, and Ieee 13 for 802.11g and 2.4. Other countries such as Spain initially allowed only channels 10 and 11, and France only allowed 10, 11, 12 and 13. However, they now allow channels 1 through 13. North America and some Central and South American countries allow only 1 through 11. Since the spectral mask only defines power output restrictions up to a plus or minus 11 MHz from the center frequency to be attenuated by a 50 dBr, it is often assumed that the energy of the channel extends no further than these limits. It is more correct to say that, given the separation between channels, the overlapping signal on any channel should be sufficiently attenuated to minimally interfere with the transmitter on any other channel. Due to the near-far problem, a transmitter can impact a receiver on a non-overlapping channel, but only if it is close to the victim receiver or operating above allowed power levels. Confusion often arises over the amount of channel separation required between transmitting devices. 802.11b was based on DSSS modulation and utilized a channel bandwidth of 22 MHz, resulting in 3 non-overlapping channels. 802.11g was based on OFDM modulation and utilized a channel bandwidth of 20 MHz. This occasionally leads to the belief that 4 non-overlapping channels exist under 802.11g, although this is not the case as per 17.4.6.3 channel numbering of operating channels of the IEEE STD 802.11, which states in a multiple cell network topology, overlapping and/or adjacent cells using different channels can operate simultaneously without interference if the distance between the center frequencies is at least 25 MHz. And Section 18.3.9.3 and Figure 18-13. This does not mean that the technical overlap of the channels recommends the non-use of overlapping channels. The amount of interference seen on a 1, 5, 9, and 13-channel configuration can have very small difference from a 3-channel configuration, and in the paper entitled Effect of Adjacent Channel Interference in IEEE 802.11 WLANs by Villegas, this is also demonstrated. Although the statement that channels 1, 5, 9 and 13 are non-overlapping is limited to spacing or product density, the concept has some merit in limited circumstances. Special care must be taken to adequately space AP cells, since overlap between the channels may cause unacceptable degradation of signal quality and throughput. If more advanced equipment such as spectral analyzers are available, overlapping channels may be used under certain circumstances. This way, more channels are available. Regulatory domains and legal compliance. IEEE uses the phrase reg domain to refer to a legal regulatory region. Different countries define different levels of allowable transmitter power, time that a channel can be occupied, and different available channels. Domain codes are specified for the United States, Canada, ETSI, Spain, France, Japan, and China. Most Wi-Fi certified devices default to reg domain 0, which means least common denominator settings, that is, the device will not transmit at a power above the allowable power in any nation, nor will it use frequencies that are not permitted in any nation. The reg domain setting is often made difficult or impossible to change so that the end users do not conflict with local regulatory agencies such as the United States Federal Communications Commission. Layer 2 are Euro datagrams. The datagrams are called frames. Current 802.11 standards define frame types for use in transmission of data as well as management and control of wireless links. Frames are divided into very specific and standardized sections. Each frame consists of a MAC header, payload and frame check sequence. Some frames may not have the payload. The first 2 bytes of the MAC header form a frame control field specifying the form and function of the frame. The frame control field is further subdivided into the following subfields: protocol version, 2 bits representing the protocol version. Currently used protocol version is 0. Other values are reserved for future use. Type, 2 bits identifying the type of WLAN frame. Control, data and management are various frame types defined in IEEE 802.11. Subtype, 4 bits providing additional discrimination between frames. Type and subtype together to identify the exact frame. To DS and from DS, each is 1 bit in size. They indicate whether a data frame is headed for a distribution system. Control and management frames set these values to 0. All the data frames will have one of these bits set. However, communication within an IBSS network always set these bits to 0. More fragments. The more fragments bit is set when a packet is divided into multiple frames for transmission. Every frame except the last frame of a packet will have this bit set. Retry. Sometimes frames require retransmission, and for this there is a retry bit which is set to 1 when a frame is resent. This aids in the elimination of duplicate frames. Power management. This bit indicates the power management state of the sender after the completion of a frame exchange. Access points are required to manage the connection and will never set the power saver bit. More data. The more data bit is used to buffer frames received in a distributed system. The access point uses this bit to facilitate stations in power saver mode. It indicates that at least 1 frame is available and addresses all stations connected. WEP. The WEP bit is modified after processing a frame. It is toggled to 1 after a frame has been decrypted, or if no encryption is set it will have already been 1. Order. This bit is only set when the strict ordering delivery method is employed. Frames and fragments are not always sent in order as it causes a transmission performance penalty. The next 2 bytes are reserved for the duration ID field. This field can take one of 3 forms: duration, contention-free period, and association ID. An 802.11 frame can have up to 4 address fields. Each field can carry a MAC address. Address 1 is the receiver, address 2 is the transmitter, address 3 is used for filtering purposes by the receiver. The sequence control field is a 2-byte section used for identifying message order as well as eliminating duplicate frames. The first 4 bits are used for the fragmentation number and the last 12 bits are the sequence number. An optional 2-byte quality of service control field which was added with 802.11e. The frame body field is variable in size, from 0 to 2304 bytes plus any overhead from security encapsulation, and contains information from higher layers. The frame check sequence is the last 4 bytes in the standard 802.11 frame. Often referred to as the cyclic redundancy check, it allows for integrity check of retrieved frames. As frames are about to be sent, the FCS is calculated and appended. When a station receives a frame, it can calculate the FCS of the frame and compare it to the one received. If they match, it is assumed that the frame was not distorted during transmission. Management frames. Management frames allow for the maintenance of communication. Some common 802.11 subtypes include authentication frame. 802.11 authentication begins with the WNIC sending an authentication frame to the access point containing its identity. With an open system authentication, the WNIC only sends a single authentication frame and the access point responds with an authentication frame of its own indicating acceptance or rejection. With shared key authentication, after the WNIC sends its initial authentication request, it will receive an authentication frame from the access point containing challenge text. The WNIC sends an authentication frame containing the encrypted version of the challenge text to the access point. The access point ensures the text was encrypted with the correct key by decrypting it with its own key. The result of this process determines the WNIC's authentication status. Association request frame. sent from a station. It enables the access point to allocate resources and synchronize. The frame carries information about the WNIC, including supported data rates and the SSID of the network the station wishes to associate with. If the request is accepted, the access point reserves memory and establishes an association ID for the WNIC. Association response frame, sent from an access point to a station containing the acceptance or rejection to an association request. If it is an acceptance, the frame will contain information such as an association ID and supported data rates. Beacon frame, sent periodically from an access point to announce its presence and provide the SSID, and other parameters for WNICs within range. De-authentication frame, sent from a station wishing to terminate connection from another station. Disassociation frame, sent from a station wishing to terminate connection. It's an elegant way to allow the access point to relinquish memory allocation and remove the WNIC from the association table. Probe request frame, sent from a station when it requires information from another station. Probe response frame, sent from an access point containing capability information, supported data rates, etc., after receiving a probe request frame. Reassociation request frame, a WNIC sends a reassociation request when it drops from range of the currently associated access point and finds another access point with a stronger signal. The new access point coordinates the forwarding of any information that may still be contained in the buffer of the previous access point. Reassociation response frame, sent from an access point containing the acceptance or rejection to a WNIC reassociation request frame. The frame includes information required for association such as the association ID and supported data rates. Information elements, 2. In terms of ICT, an information element is a part of management frames in the IEEE 802.11 wireless LAN protocol. IEs are a device's way to transfer descriptive information about itself inside management frames. There are usually several IEs inside each such frame, and each is built of TLVs mostly defined outside the basic IEEE 802.11 specification. The common structure of an IE is as follows. A1AA 1AA 3AA 1-252 type length OUI data. Whereas the OUI is only used when necessary to the protocol being used, and the data field holds the TLVs relevant to that IE. Control frames. Control frames facilitate in the exchange of data frames between stations. Some common 802.11 control frames include, Acknowledgement Frame. After receiving a data frame, the receiving station will send an ACK frame to the sending station if no errors are found. If the sending station doesn't receive an ACK frame within a predetermined period of time, the sending station will resend the frame. Request to send frame. The RTS and CTS frames provide an optional collision reduction scheme for access points with hidden stations. A station sends an RTS frame to as the first step in a two-way handshake required before sending data frames. Clear to send frame. A station responds to an RTS frame with a CTS frame. It provides clearance for the requesting station to send a data frame. The courts provides collision control management by including a time value for which all other stations are to hold off transmission while the requesting station transmits. Data frames. Data frames carry packets from web pages, files, etc. within the body. The body begins with an IEEE 802.2 header, with the destination service access point specifying the protocol. However, if the DSAP is hex AA, the 802.2 header is followed by a subnetwork access protocol header, with the organizationally unique identifier and protocol ID fields specifying the protocol. If the OUI is all zeros, the protocol ID field is an ether type value. Almost all 802.11 data frames use 802.2 and snap headers, and most use an OUI of 0 o'clock and an ether type value. Standard and amendments. Within the IEEE 802.11 working group, the following IEEE Standards Association standard and amendments exist: IEEE 802.11-1997, the WLAN standard was originally 1-bit S and 2-bit S, 2.4 a GHz-RF and infrared standard. All the others listed below are amendments to this standard, except for recommended practices 802.11f and 802.11t, IEEE 802.11a, 54-bit S, 5 a GHz standard. IEEE 802.11b, enhancements to 802.11 to support 5.5 and 11-bit S, IEEE 802.11c, bridge operation procedures. Included in the IEEE 802.1d standard, IEEE 802.11d, international roaming extensions, IEEE 802.11e, enhancements CoS, including packet bursting, IEEE 802.11f, Inter-Access Point Protocol withdrawn February 2006, IEEE 802.11g, 54-bit S, 2.4 a GHz standard, IEEE 802.11h, Spectrum Managed 802.11a for European compatibility, IEEE 802.11i, Enhanced Security. IEEE 802.11j, Extensions for Japan, IEEE 802.11-2007, a new release of the standard that includes amendments A, B, D, E, G, H, I and J. IEEE 802.11k, Radio Resource Measurement Enhancements, IEEE 802.11n, Higher Throughput Improvements using MIMO, IEEE 802.11p, Waiver Euro Wireless Access for the Vehicular Environment, IEEE 802.11r, Fast BSS Transition, IEEE 802.11s, Mesh Networking, Extended Service Set, IEEE 802.11t, Wireless Performance Prediction Euro Test Methods and Metrics Recommendation cancelled, IEEE 802.11 new, improvements related to hotspots and third-party authorization of clients. For example, cellular network offload, IEEE 802.11v, Wireless Network Management, IEEE 802.11w, Protected Management Frames, IEEE 802.11y, 3650 Euro 3700 MHz operation in the US. IEEE 802.11z, Extensions to Direct Link Setup, IEEE 802.11-2012, a new release of the standard that includes amendments K, N, P, R, S, U, V, W, Y and Z, IEEE 802.11 all, robust streaming of audio-video transport streams, IEEE 802.11 AC, very high throughput less than 6 a GHz. Potential improvements over 802.11n, better modulation scheme, wider channels, multi-user MIMO. IEEE 802.11 AD, very high throughput 60 a GHz, CW gig, IEEE 802.11e, prioritization of management frames, IEEE 802.11 ARV, TV whitespace, in process, IEEE 802.11 MC, roll-up of 802.11-2012 plus or, AC, AD, and after be published as 802.11-2015, IEEE 802.11R, sub-1 a GHz license exempt operation, IEEE 802.11i, fast initial link setup, IEEE 802.11 ARG, China millimeter wave, IEEE 802.11 ARC, general links, IEEE 802.11 AC, pre-association discovery, IEEE 802.11 AX, high-efficiency WLAN, 802.11F and 802.11T are recommended practices rather than standards, and are capitalized as such. 802.11M is used for standard maintenance. 802.11 MA was completed for 802.11-2007, 802.11 MB was completed for 802.11-2012 and 802.11 MC is working towards publishing 802.11-2015. Standard versus amendment, both the terms standard, and amendment are used when referring to the different variants of IEEE standards. As far as the IEEE Standards Association is concerned, there is only one current standard. It is denoted by IEEE 802.11 followed by the date that it was published. IEEE 802.11-2012 is the only version currently in publication. The standard is updated by means of amendments. Amendments are created by task groups. Both the task group and their finished document are denoted by 802.11 followed by a non-capitalized letter. For example, IEEE 802.11a and IEEE 802.11b. Updating 802.11 is the responsibility of Task Group M. In order to create a new version, TGM combines the previous version of the standard and all published amendments. TGM also provides clarification and interpretation to industry on published documents. New versions of the IEEE 802.11 were published in 1999, 2007 and 2012. The next is expected in 2015. Nomenclature. Various terms in 802.11 are used to specify aspects of wireless local area networking operation, and may be unfamiliar to some readers. For example, time unit is used to indicate a unit of time equal to 1024 microseconds. Numerous time constants are defined in terms of TU. Also, the term portal is used to describe an entity that is similar to an 802.11h bridge. A portal provides access to the WLAN by non-802.11 LAN STAs. Community networks. With the proliferation of cable modems and DSL, there is an ever-increasing market of people who wish to establish small networks in their homes to share their broadband internet connection. Many hotspot or free networks frequently allow anyone within range, including passers-by outside, to connect to the internet. There are also efforts by volunteer groups to establish wireless community networks to provide free wireless connectivity to the public. Security. In 2001, a group from the University of California, Berkeley presented a paper describing weaknesses in the 802.11 wired equivalent privacy security mechanism defined in the original standard. They were followed by Fleurer, Mantin, and Shamir's paper titled Weaknesses in the Key Scheduling Algorithm of RC4. Not long after, Adam Stubblefield and AT&T publicly announced the first verification of the attack. In the attack, they were able to intercept transmissions and gain unauthorized access to wireless networks. The IEEE set up a dedicated task group to create a replacement security solution, 802.11i. The Wi-Fi Alliance announced an interim specification called Wi-Fi Protected Access based on a subset of the then current IEEE 802.11i draft. These started to appear in products in mid-2003. IEEE 802.11i itself was ratified in June 2004, and uses the Advanced Encryption Standard AES, instead of RC4, which was used in WEP. The modern recommended encryption for the home consumer space is WPA2 and for the enterprise space is WPA2 along with a radius authentication server and a strong authentication method such as EAPTLS. In January 2005, the IEEE set up yet another task group W to protect management and broadcast frames, which previously was sent unsecured. Its standard was published in 2009. In December 2011, a security flaw was revealed that affects some wireless routers with a specific implementation of the optional Wi-Fi protected setup feature. While WPS is not a part of 802.11, the flaw allows a remote attacker to recover the WPS PIN and, with it, the router's 802.11i password in a few hours. Non-standard 802.11 extensions and equipment. Many companies implement wireless networking equipment with non-IEEE standard 802.11 extensions either by implementing proprietary or draft features. These changes may lead to incompatibilities between these extensions. See also, Bluetooth, another wireless protocol primarily designed for shorter-range applications. Comparison of wireless data standards, OFDM system comparison table, ultra-wideband, Wi-Fi Alliance, Wi-Fi Operating System Support, WiBRI, Wireless Gigabit Alliance, also known as WiGig, Fujitsu Limited v. Netgear Incorporated. Wireless USB, another wireless protocol primarily designed for shorter-range applications. References. External links, IEEE 802.11 Working Group, Official Timelines of 802.11 Standards from IEEE.